Okay, so for part B, we're asked to find the value of k given that the limit as x approaches 0 of f of x is equal to 16. Okay, so what happens if we directly try to take this limit by plugging in x is equal to 0 into f of x? Well, what's going to happen is we're going to get 0 over 0. Now, why is that? Because we're going to end up with sine squared of k times 0, which is sine squared of 0. And sine of 0 is just 0, and 0 squared is 0, so we're going to get 0 in the numerator. Then in the denominator, much more simply put, we're going to get 0 as well, right? 0 squared is just 0. So therefore, we have the indeterminate form of 0 over 0, and that tells us that we can use L'Hopital's rule in order to help us out here. So let's do that. Just to review, L'Hopital's rule tells us that we can take the derivative of the numerator and the derivative of the denominator, and then take the limit of the result of that, and that will be the same as the limit of our original equation. Now keep in mind, this is not quotient rule for L'Hopital. We treat the numerator as one, we take the derivative of the numerator, and then separately we take the derivative of the denominator in two separate ways. So if we take the derivative of the numerator, we're going to get 2k times sine kx cosine kx. And we can do that by using the product rule, right? Because sine squared kx is like a product. It's like sine kx times sine kx. And then the denominator is x squared, and the derivative of x squared, just with the power rule, is 2x. Now you might be thinking, oh, but aren't we going to run into the same problem again? Because once we plug in 0 again, we're just going to get 0 in the numerator, because sine of kx will be just sine of 0. And sine of 0 is 0, and multiplying 0 by cos kx and 2k will still give us 0 in the numerator. And likewise in the denominator, 2 times x, or in this case 2 times 0, is indeed just 0 again. So this tells us we actually need to apply L'Hopital's rule a second time to our result. So let's do that. Okay, so if we apply it a second time, we are going to end up getting that the limit as x approaches 0 is 2k squared times cosine squared kx minus sine squared kx all over 2, because the derivative of 2x is just 2. And then what we're going to do is now we can finally plug in 0 for x in the next step. The other thing we might notice here is that cosine squared kx minus sine squared kx is actually the same as cosine 2kx, so we could apply that trig identity, or we don't necessarily have to, right? Because in this case, even if we do plug in 0 for x, it's not like we're going to get something indeterminate anyway. So let's do that. Let's just plug in 0 for x. So we're going to get 2k squared times cosine squared of 0 minus sine squared of 0 over 2. And that's going to be 2k squared over 2, since sine squared 0 is just going to give us 0, and cos squared 0 is just going to give us 1, right? And so therefore 1 minus 0 is we're just going to be multiplying by 1 here. So this just goes away in the end. And 2k squared over 2 is just k squared. So we got that this limit is equal to k squared. Now if we go back to the question, we're also given in the question that the limit is 16. That tells us that k squared is equal to 16. So if k squared is equal to 16, therefore k is equal to 4.